5 days. And so as far as parameterizing services, so we can parameterize a curve with a single parameter, right? Curves are one-dimensional things, even though it could fill up. Let's see, annotate here. So curve, even though it could squiggle through R3, it's still just a one-dimensional thing. Given a point, there's really it's at a point, it's just linear, right? So it's a one-dimensional thing. So it takes one parameter to parameterize a curve. And we usually call that t, right? And so you have one variable t to write, if it's in R3, to write x, y, and z for all points on the curve. That's what a parameterization does. It represents all points on, in this case, on the curve. It gives us it generates all the points by different values of t. Okay, and then we said a surface then, that's like a two-dimensional, there's, surface. Given a point on the surface, there's really like 2 degrees of freedom on a surface. And so we need 2 parameters, u and v, to parameterize a surface. So we usually call that S. So now R is a function of u and v. And again, we're writing x, y, and z, each as a function of u and v. So the first thing we said was, if you have a z function of x and y, then you can just use x and y as the 2 parameters, and then write z as that formula using x and y. So those were the easiest ones. And then we said, and we did those examples. We said for a cylinder, one parameter is going to be for the cross-sectional curve of the 2 variables, and then the other parameter will be for the missing variable, taking that curve and sweeping it into the 3rd dimension. So in this case, you'll have the parameter, you'll use z and x. And so y can be written in terms of x. You'll have x and then x, e to the minus x, and z. And that will get all points on that cylinder. All right, and then we talked about circular surfaces using polar, using r and or theta. We did a couple examples of those. So now let's do this example. We didn't get to this one. The unit disk at the plane z equals 6. So we're up here at z equals 6, and we're going to do the unit disk, which is what? The filled-in circle. It's a filled-in circle at z equals 6. So we have 2 variables. We have to pick 2 variables to write every point as x, y, and z. X, y, and z. So what two variables do we want to pick for this that are the most natural pick to write every point in this disk at z equals 6?
Would it be r and theta?
Okay, so let's think about r and theta. So would r and theta get us every point on that disk? What would x be if we're in terms of r and theta? So now our r varies, right? R varies because it's a disk, it's filled in. So all r values from 0 out to r equals 1. So what would x be using r and theta?
Just be r.
R cosine theta, right? And then y is?
R sine theta.
And what would z be in terms of r and theta? What are the z coordinates of all these points?
6.
Just 6. No matter what the point is, it always has a z coordinate 6 if it's in the plane z equals 6. So I think this does it. So a disk can always be written as r cosine theta, r sine theta, and that this whole disk is at z equals 6. The last thing is just to get the boundary. So if it's only inside the unit disk, then what's restricted? Is that r restricted or theta?
R is restricted.
Between what and what?
0 and 1.
0 to 1. Questions on that? So again, we're writing every point as an x, y, z triple, every point on that disk, we get two variables to do it. So this does it. R cosine theta, R sine theta, different radii from the center, different angle, and always a height of 6, gets every point on that thing. All right, one more. So here is for spheres. So for spheres, we can use spherical coordinates to parameterize any part or a whole sphere. Rectangular coordinates are only going to be able to parameterize at most a half sphere. You can do it, but then they involve lots of squares and square roots, and it's not aligned, right? So rectangular coordinates are not aligned with spheres. So that's why we have spherical coordinates to keep the expressions simpler. And so we want a half sphere of radius 9 centered at the origin. We want to parameterize this surface, which looks like this basically. Radius 9. Okay, and so we get two variables to write x, y, and z. So we want to pick wisely here. And so how can we pick which two variables? So we know our spherical coordinates are rho, phi, and theta, but we only get two. We only get two variables to write every point on the sphere. So what will we choose? How about rho? Should we pick rho as one of our two variables for the sphere?
No, because it would be constant throughout all the axes.
Right. On every point on the sphere, rho is 9. That's the definition of the sphere. Rho equals 9 is the definition of the sphere. And so that would be, if we chose rho to be one of our variables, that'd be a waste of variable because it's always 9. Okay, so we could do this in phi and theta. So what is x in terms of rho, phi, and theta? So you have to go back and remember our spherical coordinates. So we know x is r cosine theta. That's one way to start. So we got cosine theta. So what is r in spherical coordinates? Anybody remember? It was rho sine phi. So r was rho sine phi. And so then y is rho sine phi sine theta. And what was z in spherical coordinates?
Rho cosine phi.
Yeah, rho cosine phi. Good. So there it is. And then we need restrictions. What does rho go from? What does phi go from? And what does theta go from?
Phi
Go.
to pi over 2.
Phi goes from straight up the z-axis. We got points right up there near the z-axis, all the way to
Pi.
the negative z-axis. So yeah, phi goes from 0 to pi. What about theta? So theta, it's the whole sphere in negative y territory. Should be theta from what to what?
Pi to 2 pi.
Right? This is pi. This is 0. Positive x-axis is 0. Positive y-axis is pi over 2. Pi to 2 pi. So we got it.
So in the vector, would we change rho into 9?
Oh, yes. I'm sorry. Yes, of course. Thank you. Yeah, we don't want to put rows in there. We only get phi and theta, and we know what rho is. It's always 9 on the sphere. Thank you. Yes. Questions? Okay. So we've done lots of examples of parameterizing surfaces. You got a few in the web work, and we're going to need this for what we do next, which is what we were going to start today. And what that is It's right here, and we're going to do surface integrals. So to talk about surface integrals, we want to talk about line integrals first. Let's review line integrals. And you'll see why we're going to do that. All right, so line integrals. So there were two kinds of line integrals. There was line integral of a multivariable function, which is what we'll do today, and then there's line integrals of a vector field. And we'll talk about that Wednesday. So line integrals of multivariable functions was this. We had this function, which is blue here, and then we were going to integrate it over a curve in the xy plane. So maybe like this. Something like that. So this is some curve in the xy plane. And so we only care about the points of the function f straight above that curve. Something like that. Okay? And so what did it calculate? So a line integral, our multivariable function is a 3D surface of two variables. That's our f. That's the blue function, right? That's the blue function. Over a one-dimensional curve C, right? Okay. C is parameterized as one variable, right? It's a curve, right? We know we parameterize curves with one variable. And so then this is our ds. ds. ds is a little bit of the curve, or a little teeny segment that's representing an infinitesimal or a small element of the curve. Those are our ds's. So what are we going to get when we take ds, which is little length, those little lengths, times the height, right? So the function is z. So that's the height. So a little length times height, and do that over and over again and add those all up. That's what the integral does. So we're going to take little length here along c times the height, and then we're going to add all that up. What's that going to give? What kind of thing is that going to give? What kind of quantity?
The area of the vertical surface.
Yeah, so we're going to get little area strips, right? Base, this is like base times height, right? Base times height, and then we're going to add all those up. So we're going to get this like area of this curtain. Right, so this is going to be like a curtain. Do it this way. There we go. That looks better. So we're going to get this curtain that's defined by the curve C, and the top of it is defined by this multivariable function, and we're going to get the area of that. Or if the function ever dips negative over C, then it's going to be a net area, right? It's going to be a difference of areas. So if my function had a value of 1, so suppose f had a value of 1 everywhere, so f was equal to 1, instead of the blue, this blue wavy surface, then what would the line integral give? If this was 1, then it would be the area of the curtain where the height is 1 everywhere. And what will that be the same as?
The length of the curve.
Right, because if we're taking area of the base, these little ds's, times 1, we're just going to get the ds's. If we sum up all the ds's, we'll just get the length of the curve. So you get the length of C. We saw that before with double integrals, right? If you and triple integrals, if you integrate 1 for double integral, what did you get? If that was 1, we got the area of the region in the xy plane. Triple integral, if we did 1, we got the volume of the solid. So here's the same thing here with line integrals. If you integrate 1, you'll get the length of the curve. Okay, so now that's kind of an overview of line integrals. So we've done those before. Line integrals of a multivariable function. So now, a surface integral is really the exact same thing. It's totally analogous to this. Everything is just stepped up 1 dimension. But it's the same idea, or the same, everything's parallel.
So then is it kind of like, it's kind of like to this surface integral stuff is to line integrals kind of what triple integrals are to double integrals?
Nah. No, it's not quite. It's better than that. But we didn't really see that triple integrals was the exact same thing as double integrals stepped up 1. It was a little bit different, kind of. But this is more. There's more parallelism here than that even. So here is our. So looking at the line integral of a multivariable function. We have the surface integral of a multivariable function, but now that multivariable function lives in R4 and has 3 variables. So it's a 4-dimensional surface of 3 variables, first of all. So 4-dimensional surface of 3 variables. That's F. Okay, so that we don't really draw those, right? So I'll just kind of, but it would be analogous to the blue surface. So whatever the blob is, okay. So this is F, and it lives in R4. And we're going to integrate that R4 solid over now. Here was over a curve in R2, and so now we're going to integrate that over a surface in R3, which is 2-dimensional and lives in R3. Okay, so instead of the blue 3-dimensional surface of 2 variables, now we have this this thing that I've drawn, this 4-dimensional surface of 3 variables, and instead of integrating over a curve, we're going to integrate that thing over a surface in R3. Okay, and so then the surface, instead of being parameterized in 1 variable, we know surface is parameterized in 2 variables. Okay, so we're gonna define S as parameterized in terms of 2 variables u and v, and that might be x and y, that might be z and theta, that might be r and theta, rho and phi. We have all those different examples of parameterizing surfaces. Gee whiz. Okay. All right. So S is parameterized as 2 variables, and so just like we said, ds before were little line segments along the curve. Now this is d big S. This is d at big S. Instead of 1-dimensional line segments, now we have little 2-dimensional elements that are defining the surface. So Little segments defining little lengths defining the curve, little elements defining the surface. And notice so this was the derivative. This is r prime of t. These are the partial derivatives of r. So now we have two derivatives of our surface parameterization. And we do the cross product of those. So you remember what you got when you did the magnitude of the cross product of two vectors? Anybody remember? This is back from the first week or maybe the second week of class. When you take the cross product and take the magnitude of that, that had a geometric result, the magnitude, the value. Anybody remember what that was?
Is it the magnitude of the resulting vector?
Yeah, but it's not a vector. So yes, it is, but there was a nice geometric result relative to the first two vectors in the plane.
This is the area of a parallelogram.
Yeah, it's the area of that parallelogram you get from putting those two vectors tail to tail. So if you put A and B tail to tail, that forms a unique parallelogram. The magnitude of the cross product was the area of that parallelogram. And so we, in fact, use little parallelograms to model the surface or try to recreate the surface one element at a time. And so your ds, so your d little s were lengths of the curve, and now your d big S are areas of the parallelograms that are trying to reproduce the curve, reproduce the surface. And so that's the parallelism there. Okay, so then the integral, here the integral what? Computed net area of this vertical surface. So this integral is going to compute some kind of net hyper area. It's like wherever f is positive, has a positive contribution to this value, and wherever f is negative, it's a negative contribution, but it's only for points on the surface, right? Only for x, y, and z ordered pairs from that surface are we going to accumulate our hypersurface, so we get net hyper area. But if this four-dimensional f function equals 1, then what will the integral give us? So if we let this function equal to 1 and just do the surface integral of d capital S, what will that give us? Same thing again. If this function was 1, we got the length of the curve. If this function was 1, we got the area of the surface. So if this function is 1,
You get volume.
no.
Surface area?
Yeah, we get the area of that thing, right? We get the area of the surface. But volume was a decent choice, but there's no solid, right? There's no solid. We're integrating over a surface, not a solid. So yeah, if you let f equals 1, then just like the other things, you're going to get the area of that yellow patch. Okay, so really, these surface integrals are exactly like line integrals in pretty much in every single way. Everything stepped up one dimension. And so this is one of the biggest applications of these. Using these surface integrals to compute surface area. And so you can do it for all kinds of weird shapes in R3.
Why can a two-dimensional surface exist in a three-dimensional place?
We've been doing that all semester. Paraboloids, planes, spheres. That's exactly all these things, right? It's two-dimensional. Okay, so it's two-dimensional because for points on the surface, there's only 2 degrees of freedom. Like on that point, you can define all the points around it with just 2 variables. A component going this way and a component going this way. Does that make sense? So it's like if you take like a plane is a two-dimensional surface. If you warp it, if you curve it, if you meld it, it lives in a three dimensions, but the surface itself is still two-dimensional. It's just warped. Does that help?
Okay, that makes more sense.
Yeah.
Thank you.
Yeah. So the point is it's two-dimensional because you can define every point on a surface, even if it's in R3. You can define every point with two variables. It only takes two variables to do it, and that's what we did on Wednesday at the beginning of class today. Okay. Other questions? All right. Let's look at some examples. Okay, so the first thing we want to talk about is we talked about given a surface, right? Given an equation of x, y, and z, can you write it parametrically? That's what we did Wednesday and a little bit at the beginning of today. So then the other thing that's important is going the other way around. So this now is, say, given a surface defined parametrically, can you write it as a single equation of x, y, and z? We know that's our surfaces, right? Single equations of x, y, and z. That's how we talked about surfaces all semester. Now we're also talking about surfaces not only as a single equation of x, y, and z, but parametrically. We can define it parametrically using two parameters. So that both now work for defining a surface. So given the parametric version and two variables, can you write it as a single equation x, y, and z? So here, this one we have u cosine v, and for cosine and sine, I'm just going to write c and s. And u sine v. So what's our goal? So this is x equals u, y equals u cosine v, and z equals u sine v. So our goal is to combine these. We got three equations. To combine them to eliminate u and v and get a single equation of x, y, and z. So we've done this before with the parametric functions of one variable, the curves. So it's the same techniques, but now we just have two variables to eliminate. So looking at y and z here, anybody see how we can eliminate v? What the natural way to eliminate v is? Because I got a cosine v and a sine v. What's the natural way to eliminate?
They're magnetic. Like wrap them up into a theta.
Well, that v is kind of like theta, right? So like u is kind of like r, and v is kind of like theta already. So what if you have cosine and sine? What's the key to kind of eliminating that?
Relate them to the equation of the circle.
Maybe u square and u cube.
Okay, haven't heard it yet.
X would be cosine v and y would be sine v.
No, I want to eliminate. I want to do something with the cosine and sine so that they go away.
Cosine v could be the u, maybe.
No, this.
V.
No, it's still v. You still tangent. You still have v. Anybody?
Cosine?
No, we don't want that. We don't want inverse cosine or sine.
Cosine squared plus sine squared is 1.
Thank you. Pythagorean identity, right?
What I say?
So how do we get? Well, we can't just square those. They have u's attached to them. So if we square y and we square z, that will get our cosine squared and our sine squared. So let's do that. So we do y squared plus z squared. That'll be u squared cosine squared v plus u squared sine squared v. Which is u squared times cosine squared v, which is u squared. So we got rid of v, but now we still have u. What is u?
X.
U is x. So u squared is?
X X squared.
X squared. So in the end, we got x squared equals y squared plus z squared. So I added squared and added y squared and y and z because I knew that would get me cosine squared and sine squared involved. And I factored out my u squared, and then this is 1. And I got y squared plus z squared equals u squared, but u is x, so that's x squared. So what do we have? So now you have to know your surfaces, like we learned for test 1 and 2.
Oh,
Double cone. Okay, does that make sense? So that's a really important technique for trying to eliminate cosine and sine using the Pythagorean identity. All right, let's do a surface integral then, example. Okay, so here's one. So they want us to evaluate, so we know that our surface integrals are of this form. And so it looks like our multivariable function here is the square root of 1 plus x squared plus y squared. And we know that ds is what? Ru cross Rv, du dv. Okay, and so to do a surface integral, we have to rewrite the whole function in terms of u and v. So we're going to find everything in terms of u and v, and that includes this function here. So here they're giving us the parameterization. That's very nice. And a helicoid is like a spiral ramp. It's kind of like an auger, if you know what an auger is. So it's a surface that looks kind of like that, where this is the surface here.
Is that the one where it gets bigger? Or?
This does not get bigger. It extends infinitely out this way, but the radius doesn't get bigger.
Oh, okay.
But it's kind of weird, right? So the radius is infinite everywhere, so it's not like a cone shape, if that's what you mean. But this extends out everywhere. It's just to draw it, you can only draw so much of it. So it keeps going up, but then the ramp itself is infinitely wide. Okay, so we've got the parameterization of that spiral ramp, and so we're just going to apply our surface integral. So what's 1 plus x squared plus y squared? It's going to be square root of 1 plus, what is x?
U cosine v.
So we're going to do that squared, right? And then u sine v squared. So now we have to find what? The partial derivatives of our parameterization, do the cross product, and take the magnitude. So we'll do that over here. So we're going to do cross product, so that means I, j, and k. And then we're going to do partial with respect to u, partial with respect to v. So the partial with respect to u is each one separately, we get
Cosine v.
cosine v,
And
sine v, and
or 0.
0. And now with respect to v, we're going to get negative u sine v, u cosine v, and 1. And now we're going to do the cross product. So the cross product is going to be, so this is going to be positive sine v this way, down this way, and then 0. So all we get is sine v for I. J, going down to the right is 0. Down to the left will be negative cosine v. K, we'll have two terms. we'll go down to the right, so we'll have u sine squared, or sorry, u cosine squared, and then minus negative u sine squared. So plus u sine squared. So that's our cross product. And then we need the magnitude of it. So then the magnitude is going to be the square root of sine squared v plus negative cosine squared v. And before we square this thing, let's figure out what does this equal right here.
U squared.
U squared.
Just yeah, the z component is just u, and then we're going to square it. So in here it's u squared. And then what do we got here? Sine squared plus negative cosine squared. That's going to equal 1. And then, so we're going to end up with, for that magnitude of that cross product, it's going to be 1 plus u squared. So what is this?
U squared.
Also u squared. So look, we got square root of 1 plus u squared times square root of 1 plus u squared. What does that equal?
1 plus u squared.
Just 1 plus u squared, right? And then we just got to decide what is, so u goes from what to what? Tell us. And v goes from 0 to 5 pi. Questions on this example? So we're going to rewrite our function in terms of u and v. We're going to get the partial derivatives and do the cross product and take the magnitude of that. Then we're going to multiply that times the function and set the limits.
Yeah, I'm confused where you get the negative in the in your cross product for rho or r of v rho. So the negative u sine v.
Oh, that's the partial derivative of x with respect to v. So derivative of cosine v. Right, we're doing partial derivatives, so we're differentiating with respect to v. Did I answer it?
Yeah, thank you.
Yep. Other questions? Okay, so the next one has us find a surface area of this helicoid. So let's just talk about it briefly. How would we find, say, the surface area, the actual area of the helicoid for these bounds? What would be different?
You would set the, yeah, go ahead.
Let's just set f to 1, so it'd just be the square root of 1 plus u squared, and take that integral.
Right, this right here, if this thing right there, the function equals 1, then what we get, if it doesn't equal 1, but if it were to, if we just made this 1, it'd be a new problem, a different problem, we'd be changing the problem, and the surface integral would give us the surface area of this spiral ramp for these bounds. Questions on this example? All right, let's do something else. All right, let's try this. Let's make some room. It's going to be a long problem if we have time for it. We'll just get it started, okay? So we want to find the surface area of the part of the sphere that lies above the cone. So let's draw a picture over here. So our sphere is radius 4, And we know this is our standard upward opening cone.
Are we gonna have a little quiz today, or?
Yep.
Okay.
So the part of the sphere that lies above the cone is this cap here. And it wants us to find the surface area of that cap using a surface integral. Okay, so here we go. So first we gotta parameterize the surface. So we know our surface area will be 1 times u cross RV du dv, and then we'll have to get our bounds in terms of u and v. So we're going to parameterize the sphere. So how do we parameterize a sphere of radius 4? What two parameters are we going to choose?
And rho.
In theta.
Phi and theta. And we got a radius of 4, which is rho, right? Rho equals 4. So we'll have what? 4 cosine theta sine phi cosine theta, and then 4 sine phi sine theta, and then 4 cosine phi. Okay, and then we want that only for the part of the sphere here, so that is going to be, so that's just a matter of, that part of the sphere is just a matter of what our limits are. So what angle phi is equivalent to that cone right there? Do you remember? Standard reference cone?
0 to pi over 4.
Yeah, this is equivalent to, if you do the math, it's equivalent to phi equals pi over 4. Because this is z equals r. Z equals r means that rho cosine phi equals rho sine phi. So if cosine phi equals sine phi, that's phi equals pi over 4. So our limits are going to be from 0 to pi over 4 for phi, and then 0 to 2 pi for theta. So really all that's left is this bad boy, and it's bad. So we'll just get started here. So we got I, J, and K. So r phi and r theta, we need the partial derivatives. So r phi is going to be 4 cosine phi sine theta, and then 4 cosine phi, cosine theta, this is cosine theta. 4 cosine phi sine theta, and then negative 4 sine phi. Check my math. And then for theta, we'll get negative 4 sine phi sine theta, and then 4 sine phi cosine theta, and 0. Okay, ready to do the cross product. So I luckily gets a 0 to cancel out here, and then we're going to get plus 16 sine squared phi cosine theta. Not too bad so far. J gets a cancellation going down to the left. Down to the right, we get positive 16 sine squared phi sine theta. K is the ugly one. We're going to get 16 what? Cosine phi sine phi cosine squared theta. And then plus 16 cosine phi sine phi sine squared theta. And now we have to take the magnitude of that. So let's simplify this first. How does this simplify right here? I can factor out 16 cosine phi sine phi, and I'm left with cosine squared plus sine squared. So that's nice. We just get 16 cosine phi sine phi. And so the magnitude of that is the square root of 16 squared sine to the 4th phi cosine squared theta plus 16 squared sine to the 4th phi sine squared theta. Notice. Plus 16 squared cosine squared phi sine squared phi. So we're going to get the Pythagorean theorem twice here. We get it here. And so this is going to just be 16 squared sine to the 4th. And then we can factor out a 16 squared sine squared, and we're going to get another, get it again. So I can do those all in one step. So 16 squared times sine squared phi times sine squared phi plus cosine squared phi. So in the end, we get 16 sine of phi for the magnitude of the cross product. So we get lots of cancellations with Pythagorean identity.